Hello everyone, my name is Minuk. Today I'm going to talk about a paper named Obfuscated Gradients Give a False Sense of Security, Circumventing Defenses to Adversarial Examples. So basically it's about adversarial attack. It succeeded in attacking 7 out of 9 all adversarial defense papers published in ICLR 2018. Now let me explain the problem. The problem is to construct adversarial examples with iterative optimization based methods. The goal is to circumvent common defense methods, and it assumes white box attack. White box attack means, as opposed to black box attack, the attacker knows the model parameters of target. So before we move on to the details of the algorithm and the proposed method, let me briefly review adversarial attack. If we add little noise to the input, then with some conditions, we can make the classifier works incorrectly. Here is an image of a panda. If we add this kind of noise to the image, then to human eye, it just looks like panda. However, the neural network classifies it as a gibbon, a monkey. The point here is we are adding a noise that is not visually different to human eye, but totally different to neural network. Here, it's 0, the original image in MNIST data. If we add some noise, the classifier classifies it as 5. Here's the image of 3. We can make it classify as 8. While this may not seem to be so important in the case of MNIST dataset, if this kind of attack is performed on traffic signs for autonomous vehicles, it's going to be a huge problem. White box attack means the attacker knows the model, and black box attack means the attacker doesn't know the model. Usually in black box attacks, the attacker builds a model that can imitate the black box model and then applies any kind of white box attack. So let's talk in a mathematical way. Given an image X and a classifier F, an adversarial example X prime satisfies those following two properties. First, X and X prime is small for some distance metric. So they look similar, but the second condition says the classifier misclassifies them, misclassifies the adversarial example. So far, so good. But how do we make something like that? Generate adversarial examples. One popular method is Iterative-Optimization Attack. So we apply gradient ascent over the input image to maximize any class score. So here is an image of a duck and neural network, which is already pre-trained. We can calculate the probability of horse given this image and neural network theta. We can calculate the gradient with respect to this score to maximize it, and then flow this gradient back to the original input image, but not on the parameter. And we apply gradient descent or ascent, whatever else. Then the input image will change, but if we control the step size, it won't change too much. The result is, without changing it too much, we can make it classify as horse, but not dog. So after training, we add to the input image some noise, and then it becomes horse. And this kind of attack can be expanded to other types of data like speech. So this is a crucial problem. Then how do we defend against it? The previous methods usually focus on gradient masking. So to generate adversarial examples, it is necessary to apply gradient ascent or descent on the input image. But if we somehow can cut the gradient flow or mask it so that maximizing this objective is not achievable, then we can defend the attack. So it says I'm not affected by the gradient in any way. And this mask cuts the gradient flow. There are two types of it. One is shatter gradients, which is adding non-differentiable component to neural network. Since it's non-differentiable, we cannot directly apply gradient descent or ascent to the input image. The second type is stochastic gradients, which is adding stochastic component, usually around here, the input layer, to randomize gradient flow. These two together are called obfuscated gradients. However, unfortunately, what this paper proposes is such gradient masking is easy to break. For shattered gradients, which is adding non-differentiable component to neural network, they propose backward pass differentiable approximation. It is just approximating the non-differentiable component as similar differentiable component. Easy. Well, and in backpropagation, they just use the differentiable approximation function. For stochastic gradient, they apply expectation over transformation and learn to transform the adversarial example. Let me explain these two later. The first attack is backward pass differentiable approximation. So replace the non-differentiable component by similar differentiable component at backprop. Let f be f1 through j be a neural net, and let fi be a non-differentiable layer. So these indices means layer. To apply BPDA, we first have to find an approximation function, gx, which approximates the non-differentiable layer fix. How do we find it? It's up to you. It's problem specific. Let's just assume that we have find such a function. Then in the forward pass, we just use fi layer in the original network. And in the backward pass, when we apply gradient ascent on the input image to generate adversarial example, we use G. The second attack type is expectation over transformation, or EOT. EOT itself was actually introduced in previous papers, but this paper reproposed expectation over transformation to attack previously known adversarial defenses. Some defenses apply randomized transformation to the inputs, such as random rescale, random resize, etc. How do we defend adversarial attack with such randomized transformations to the input? Let me explain it later. But let's just assume that such randomized transformation to the inputs are effective in defending adversarial attack. Now, if we do that, gradients through stochastic layers are randomized so that we can cut the gradient flow. Normal attacks, which is described by this formula, where we want to find x prime, which maximizes this, can't generate adversarial examples with change in input. So EOT use affine transformation that changes adversarial example x prime. So EOT has this objective this solves this optimization problem, where the only change is this transformation and expectation. Here, still, the transformed original image and the transformed adversarial example should look similar. Now let me explain some case studies of attack with BPDA and EOT. There are 3 things. There are actually more case studies in the paper, but let me only explain the important results. One is thermometer encoding, attack on thermometer encoding. Second is attack on input transformations. And third is attack on mitigating through randomization. Actually, the second and the third are almost similar. So the first is attack on thermometer. Given an image X, for each pixel color XIJC, the L-level thermometer encoding tau is a L-dimensional vector, where tau is 1 if this is satisfied and 0 otherwise. You don't have to understand this fully. It's just discretizing the pixel values. For example, for a 10-level thermometer encoding, tau of pixel value 0.66 becomes something like this. Well, you can use one-hot encoding as well, but this thermometer encoding paper claims that their encoding method is more effective in defending adversarial attack. Due to the discrete nature of thermometer encoded values, it is not possible to directly perform GD on a thermometer encoded neural network. So basically, it introduced some layer which is not differentiable. And after the pixel values are discretized, although you input some noises to the pixel values, they are quantized. Then the noises are gone away. In that sense, the adversarial attack becomes weak. But what BPDA does is first find a G function which can replace the thermometer encoding in a differentiable manner. It's hard to find this kind of function, but anyway, they found this. And then the original L-level thermometer encoding function tau can be expressed like this, using tau hat, which is now piecewise differentiable like ReLU. Then in the forward pass, we just use thermometer encoding, and in the backward pass, when we want to apply gradient ascent on the input image, we can differentiate this function. Now let's look at attack on input transformations. So there are some previous defense methods that use transformation G to transform input X. So neural network H doesn't get X, it gets transformed input GX. And they use stochastic function G. So it's probabilistic function, like random cropping, random rescaling, bit depth reduction, JPEG compression, total variance minimization, and image quilting, etc. Many things on the input. So how does this kind of thing can defend against some adversarial attack? Let's look at a specific example. So suppose there is an input image, and we'll use 2 kinds of random transformations. One is random resize, and another is random padding. So the input image is randomly resized, and after that, we apply random padding. Then we have a whole bunch of transformed inputs, which to our eyes look very similar to the original image. And we select randomly one pattern from this set of images, and then feed that through a neural network. If we train neural network in this way, it's hard to attack this network with optimization-based adversarial attack. So for example, this is a car. So the output score for car is going to be very high, but we want it to be misclassified as airplane. So let's calculate the loss function or score function for airplane and take gradient and send gradient flow to this image and change this image. So let's assume that we have attacked this image with 500 iterations of gradient ascent. Okay, then, well, for this specific image, it's going to work. But next time, the model will see another image. There's very low probability that the same exact input image will be fed into the neural network. But we cannot cover all these. We cannot attack every single images with iterative-based method. Therefore, the attack is of no use. But what EOT says is there's a solution. How do we attack this kind of thing? Calculate the gradient for all transform samples. Okay, so take gradient for this, okay, for some samples, and take the mean of all gradients. Then we'll get some kind of noise image, right? And apply that noise image to the input image. Okay, then we are basically changing the input image xn. Before we tried to change this, but now we are changing this. So after some iterations, we'll end up in making an adversarial example which looks like this, but actually with some noise. So after we transform that generated adversarial example with these transformations, then the adversary will work. That is what EOT is saying. In this way, we can attack some defense methods that apply random transformations to the input. So the conclusion is this paper proposed two methods. One is one is BPDA, backward pass differentiable approximation, and another is expectation over transformation, EOT. The first one is for attacking some defense methods that apply non-differentiable layer to the neural network. And the second one, EOT, is for attacking defense methods that apply stochastic layers in neural network. So this paper demonstrated that those kind of gradient masking defense methods are ineffective, are easily breakable. So avoid relying on obfuscated gradients as defense method. And they released their all codes publicly available. And as I said, they succeeded in breaking 7 out of 9 all adversarial defense methods published in ICLR 2018. Thank you.